Hello, we are Group 2, composed of Angelo Heradez, Reyes, Xyrus Salvosa, and Jenoah Somera, here to provide a tutorial on the convective heat transfer coefficient for external flow across cylinders and spheres. This tutorial will first provide a brief introduction on the topic alongside the discussion on certain concepts and constants, before moving on to sample problems for better understanding and practice.
Let us then begin with the background. External flow across cylinders and spheres is seen in both industrial and day-to-day settings, from the external flow present in shell and tube heat exchangers to the effect experienced by kicked soccer balls and launched golf balls. Despite the various settings, these actually have quite similar concepts in play. One such concept present in both settings is the Reynolds number. The Reynolds number is a dimensionless number that aids in the categorization of fluid systems wherein the velocity or flow pattern of a fluid is affected by viscosity. It is essentially the ratio between the inertial forces and the viscous forces. The Reynolds number is calculated by the equation NRE equals VD over V, wherein the big V is the uniform velocity of the fluid as it approaches the cylinder or sphere. D, in this case, is the characteristic length of a circular cylinder or sphere, which is taken as the external diameter, and small v as the kinematic viscosity, or it can be represented by the other form of rho Vd over mu, wherein rho is the fluid density and mu is the fluid density. For flows across circular cylinders and spheres, the critical Reynolds number is about 2 times 10 to the fifth, and numbers below that show a laminar flow, while numbers above it show a turbulent flow. Cross-flow over cylinders exhibit flow patterns as seen here in figure 716. Fluid that approaches branches, then encircles the cylinder. A boundary layer is formed that wraps around the cylinder. Fluid particles that strike the mid-plane hit a point called the stagnation point. Fluid at that point stops and thus causes a rise of pressure there. The pressure decreases following the flow direction, while conversely, the fluid velocity will increase. At low velocities, the fluid completely wraps around the cylinder or the body, and the two arms meet on the rear side in an orderly manner, meaning that the fluid follows the curvature of the body. While for higher velocities, the fluid is too fast to remain attached to the surface as it approaches the top and bottom of the body. This results in the detachment of the boundary layer and the formation of a separation region behind the body. This hosts a wake region that follows, wherein the flow here is characterized by a random vortex formation and pressures lower than the pressure at the stagnation point.
Now it is time to discuss the drag coefficients of the figures. With that said, the drag coefficient varies depending on the Reynolds number found in the behavior of the flow. The friction drag attributed to this is caused by the friction drag when there is low Reynolds number or RE is less than 10, and the pressure drag when the Reynolds number is high, RE is greater than 5,000. In between this range, both friction and pressure drags are significant in causing the drag force. Based on figure 7-17, you can see the curve of the drag coefficient versus the Reynolds number. For the lower values of Reynolds number, or RE is less than or approximately equal to 1, it is shown that there is a decrease in the drag coefficient as the Reynolds number increases. With a case of a sphere, the drag coefficient can be calculated using the equation CD is equal to 24 over the Reynolds number. When the Reynolds number is equal to 10, the separation from the rear of the body starts to occur. This region of the separation increases as the Reynolds number increases as well. This still shows a downward trend when it comes to the drag coefficient. Further increasing the Reynolds number within the range of 10 raised to 3 to 10 raised to 5 shows a relatively constant trend with the flow along the boundary region being laminar and the flow of the separation region being highly turbulent. Finally, at the very last portion of the curves, there's a sudden drop in the drag coefficient due to the boundary layer of the body becoming turbulent as well, and the separation region becomes narrower and moved further to the back of the body.
Next up, let us talk about the effect of surface roughness. In general, surface roughness will increase the drag coefficient in turbulent flow. However, for blunt bodies such as cylinders and spheres, an increase in surface roughness may actually decrease the drag coefficient. Take this example of data for a rough surface and smooth surface sphere. At a Reynolds number of 10 to the fifth, the drag coefficient for the rough sphere is 0.1, while the smooth one has a value of 0.5. In this case, roughing up the surface reduced the drag coefficient by a factor of 5. How is this then achieved? This is done by tripping the flow of the fluid to a turbulent flow at a lower Reynolds number. This causes the fluid to close behind the body, which results in a narrower wake, conversely reducing the pressure drag considerably. This ultimately results in a smaller drag coefficient. Roughening up the surface can be used to reduce drag, but we must be careful as to operate in the right range of Reynolds number. Take the previous set of data in figure 720. In the case of Reynolds number at 10 to the 6, the drag coefficient for the rough sphere is at 0.4, while the smooth surface one is at 0.1. In this case, roughing up the sphere will increase the drag coefficient by a factor of 4. Let us analyze this deeper. Here we have a figure showing the effect of the Reynolds number on the drag coefficient of a smooth sphere. As seen, at lower values of the Reynolds number, the drag coefficient is quite significant. However, as the Reynolds number increases, we then see a steady decrease in drag coefficient values until we hit a plateau in the values at about 10 to the third to 2 times 10 to the fifth. In this range, we could consider that the drag coefficient is nearly independent of the Reynolds number. As we then keep increasing the Reynolds number, we will hit a sudden drop in the values of the drag coefficient at about 2 times 10 to the fifth to 4 times 10 to the fifth. This sudden drop is called the drag crisis, where the boundary layer separates from the surface of the sphere. From 2 times 10 to the fifth and beyond, the laminar boundary layer transitions to a turbulent boundary layer. Turbulent boundary layers are more resistant to separation from the sphere surface, which then results to a narrow wake region, which then corresponds to a lower drag coefficient value. However, sometimes it is desired to reach the drag crisis area as to achieve fast travel for spheres or balls, especially in sports. However, there are cases where the Reynolds number present is not sufficiently high enough to even reach the start of the drag crisis naturally. Thus, the solution presented is to apply artificial roughness on the surface. For golf balls, this may come in the form of dimples, and for baseballs, threaded seams. The disturbance in flow due to the roughness present prematurely transitions the boundary layer from a laminar one to a turbulent one. And such, it can force the drag crisis to occur even at a Reynolds number significantly lower than 2 times 10 to the fifth. In the case of dimpled golf balls, the critical Reynolds number is 4 times 10 to the fourth, which is lower than 2 times 10 to the fifth. Occurrence of turbulent flow at this value, which we note is lower than 2 times 10 to the fifth, causes the drag coefficient to be reduced as seen here in the figure.
This portion discusses the Nusselt number of circular and spherical bodies. Looking at figure 7-22, we can see the curves of different Reynolds number in a graph of the Nusselt number versus the increase in the angle from the stagnation point, represented by the Greek symbol theta. All of the Nusselt number of all flows start relatively high, but behaves differently depending on the Reynolds number. For the curves of the flows with Re equals to 7,800 to 101,300, there are similarities in its behavior as the angle increases. It decreases in its heat coefficient due to the thickening in the boundary layer. Then it reaches a minimum at the approximately 80 degrees due to the separation point of the laminar flow. This then begins to rise as there is an intense mixing at the wake region. As for the ones with the value of Re equal to 140,000 to 219,000, there is a change in the behavior of the curves. This is because of the curves reach 2 decreases and 2 increases as the angle increases. At the first sharp increase, this reached at around 90 degrees, where there is a transition from laminar flow to turbulent flow. The second low point is reached due to the thickening of the bound layer again, until it reaches an angle of 140 degrees, which is the turbulent flow's separation point. After this, it increases due to the mixing of the wake region. Churchill and Bernstein proposed relation for the Nusselt number of a cross flow over a cylinder. This is seen in equation 7-35 in Sengel's heat transfer textbook. This correlation correlates well with Reynolds number data and Prandtl number of greater than 0.2. Fluid properties from this equation are evaluated at the film temperature, Tf, or the average temperature of the free stream, T infinity, and the surface temperature, Ts. This is shown as follows. In addition to this, a different equation is to be used if the flow is across the cylinder. This is expressed as follows, where n is equal to 1 over 3 and constant C and M are given in table 7-1. This may be used alternatively, but with equation 7-35 being more accurate, it is more preferred in calculations. This is table 7.7-1. Similarly, a relations as also proposed for a sphere which is only valid for the range of the Reynolds number from 3.5 to 80,000 and a Prandtl number range of 0.7 to 380. Fluid properties are evaluated at the free stream temperature, T infinity, except for the value of mu sub s, which is at the surface temperature. The equation is shown as follows. Both relations are accurate, but it is common to have the result that is off about 30%.
Now, to test our knowledge, let us solve some sample problems. Our first sample problem is a scenario on a heat loss from a steam pipe in the air. The problem reads, a long 15 centimeter diameter steam pipe whose external surface temperature is 120 degrees Celsius passes through some open area that is not protected against the winds. Determine the rate of heat loss from the pipe per unit of its length when the air is at 1 atm pressure and 20 degrees Celsius, and the wind is blowing across the pipe at a velocity of 12 meters per second. The problem was illustrated as shown on the figure displayed on the screen, with its corresponding given. Air is at 20 degrees Celsius and 1 atm with a uniform velocity of 12 meters per second. The diameter of the cylindrical stem pipe is 15 centimeter or 0.15 meters, with a surface temperature of 120 degrees Celsius. We are required to solve for the rate of heat loss from the pipe per unit of its length. For the assumptions, we assume that the heat transfer operates at steady-state conditions, where radiation is neglected and air is considered as an ideal gas. To start off, the average film temperature was acquired by getting the mean of the surface temperature of the cylinder and temperature of air. This is because the fluid properties are supposed to be calculated at the average film temperature for cylinders. After calculating, we acquired an average film temperature of 70 degrees Celsius. Next, we acquired the properties of air at this solved temperature and at P is equal to 1 atm from the book. The density at these conditions is 1.028 kg per cubic meter, while the dynamic viscosity is 2.052 times 10 to the negative 5 kg per meter second, which gives a kinematic viscosity of 1.995 times 10 to the negative 5 square meter per second, and this will be used in solving for the Reynolds number. Consequently, the thermal conductivity at these conditions is 0.02881 watts per meter Kelvin, and the Prandtl number is 0.7177, which is greater than 0.2. Next, we solve for the Nusselt number for cross flow over a cylinder. Since we have acquired the average film temperature and the Prandtl number of the fluid is greater than 0.2, we can use equation 7-35 from Sengel in order to calculate the Nusselt number. Take note that this equation gives a quite accurate result but can be off as much as 30% as mentioned by Jenoah Somera. Substituting the Reynolds number and Prandtl number to the equation, we get a value of 201.93 for the Nusselt number. Next, we solve for the heat convective coefficient using the acquired Nusselt number and inserting the values of the diameter and thermal conductivity constant to the equation. Doing so, we get a value of 38.78 watts per square meter Kelvin. Finally, we solve for the rate of heat loss from the pipe per unit of its length using equation 7-9 from Sengel. Take note that AS refers to the surface area of the steam pipe, which is cylindrical in shape. Therefore, AS is equal to pi dl. This is substituted to the formula and is derived in order to arrive to the equation as shown on the screen. Substituting the corresponding values such as the diameter, the acquired heat convective coefficient, and the surface and air temperatures, we get a value of 1,827 watts per meter. If we use 1 meter as our basis, the heat transfer rate is equal to 1,827 watts. And for our second sample problem, this problem is a scenario on cooling of a steel ball by forced air. The problem reads, a 30 centimeter diameter stainless steel ball with a density of 8,055 kilogram per cubic meter and a specific heat capacity of 480 joules per kilogram degree Celsius is removed from the oven at a uniform temperature of 350 degrees Celsius. The ball is then subjected to the flow of air at 1 atmospheric pressure and 20 degrees Celsius with a velocity of 5 meter per second. The surface temperature of the ball eventually drops to 210 degrees Celsius. Determine the average convection heat transfer coefficient during this cooling process and estimate how long the process will take. But for a correction, instead of 5 meter per second, we will use the value of 4 meter per second for the uniform velocity. And this is shown in the next slide. The problem was illustrated as shown on the figure displayed on the screen with its corresponding given. Air is at 20 degrees Celsius and 1 atmospheric pressure with a uniform velocity of 4 meter per second. The diameter of the sphere ball is 30 centimeters or 0.30 meters with a surface temperature of 350 degrees Celsius. The density and specific heat capacity of the sphere were also given, which are 8,055 kilogram per cubic meter and 480 joules per kilogram degree Celsius, respectively. Lastly, the surface temperature of the sphere after cooling was given with a value of 210 degrees Celsius. We are required to solve for the average convection heat transfer coefficient and the time of cooling. For the assumptions, we assume that the heat transfer operates at steady-state conditions where radiation is neglected and air is considered as an ideal gas. Also, the outer surface temperature is uniform at all times. To start off, we acquire the properties of air at 20 degrees Celsius and at P equals 180 m from the book. The density at these conditions is 1.205 kilogram per cubic meter, while the dynamic viscosity is 1.825 times 10 to the negative 5 kilogram per meter second, which gives a kinematic viscosity of 1.516 times 10 to the negative 5 square meter per second, which will be used in solving the Reynolds number. Consequently, the thermal conductivity at these conditions is 0.02514 watts per meter Kelvin, and the Prandtl number is 0.7309. The dynamic viscosity at surface temperature of 350 degrees Celsius was also acquired and is equal to 3.101 times 10 to the negative 5 kilogram per meter second. This value is significant in solving the Nusselt number. Furthermore, the Reynolds number was calculated to be 98945 after substituting the corresponding values as shown on the screen. Next, we solve for the Nusselt number for cross flow over the sphere. We can use equation 7-36 from Sengel in order to calculate this. For this equation to be valid, the following conditions must be met. First, the Reynolds number must be in between the values of 3.5 and 80,000. Since our Reynolds number is 79,156, this condition is satisfied. On the other hand, the second condition is that the Prandtl number should be between the values of 0.7 and 380. Since our Prandtl number is 0.7309, this condition is also met. Therefore, equation 7-36 is applicable to be used. And take note that this equation also gives a quite accurate result, but can also be off as much as 30%. Substituting the Reynolds number, Prandtl number, the dynamic viscosities to the equation, we get a value of 174.42 for the Nusselt number. Next, we solve for the heat convective coefficient using the acquired Nusselt number and inserting the values of the diameter and thermal conductivity constant to the equation. Doing so, we get a value of 14.62 watts per square meter Kelvin, which is the first required to the problem. Then, we solve for the rate of heat loss from the sphere. Take note that the area refers to the surface, AS refers to the surface area of the steam pipe of the sphere, which is of the ball, which is spherical in shape. Therefore, AS is equal to pi d squared. Take note also that we are solving for the average rate of heat transfer to avoid the complexity of the changing of the temperature of the surface during cooling. Therefore, the average of both surface temperatures must be used. Substituting the corresponding values such as the diameter, acquired heat convective coefficient, and the surface temperature and the surface and air temperatures, we get a value of 1075 watts or joule per second. Then, we solve for the total heat transferred from the spherical ball as it cools from 350 degrees Celsius to 210 degrees Celsius using the formula shown on the screen. Take note that the mass is equal to the density times the volume. Substituting the corresponding values, we get a value of 7,652,391 joules. And finally, we solve for the time of cooling by dividing the total rate of heat transfer over the average rate. Therefore, we get a value of 7,119 seconds or 1 hour and 58 minutes for the time of cooling. And that's it for our presentation. Here are our references and our contributions. Thank you for listening and God bless.